Here it is, our last mini lecture for the urinary system. We have one thing to get through, and that is looking at hormonal control mechanisms for the urinary system. So without further ado, let's just get right down to brass tacks. I don't know why I said that. Anyways, okay, so our first and major hormonal mechanism for control of urine production is going to be very important and very commonly discussed, especially in the medical field. You may have heard of the RAA pathway. You may have heard of any of these terms. So renin, angiotensin, and aldosterone. This is an endocrine. Whoa, that didn't work at all. What just happened? Why is this not writing? What did I do? Anyways, the RAA pathway, and that again stands for renin, angiotensin, and aldosterone. What happens here is that we have baroreceptors that are located in quite a few places. They're a lot of times sort of around the heart and headed up towards the head. They are going to detect a drop in systemic blood pressure. When that happens, they are going to stimulate the sympathetic nervous system, which ultimately triggers the release of renin by those granular cells or those juxtaglomerular cells of the kidney. Put that here so we are consistent with our terminology. Once renin has been secreted by the kidneys, it is going to be converted to angiotensinogen. Notice that this is an ogen, which means that it is a precursor enzyme. It is not a mature or active enzyme at this point. It is going to be converted into angiotensin 1. Angiotensin 1 goes to the lungs, where there is an enzyme called angiotensin converting enzyme, also known as ACE. Maybe you've heard of ACE inhibitors. ACE inhibitors are a common treatment for blood pressure issues. But so we have angiotensin converting enzyme in the lungs, which converts this angiotensin 1 into angiotensin 2. Angiotensin 2 is what we call a potent vasoconstrictor. That is going to cause systemic vasoconstriction, so a increase in blood pressure when we get constriction. We are going to also then stimulate secretion of aldosterone and secretion of ADH. Okay, now I know I breezed through that like super fast, so let's walk through it over here. Remember, we're starting in the kidneys where we have our granular cells. They contain renin. They secrete renin in response to a decrease in blood pressure. So we have systemic blood pressure drops. Systemic blood pressure drops are going to stimulate our sympathetic nervous system. Sympathetic nervous system is going to act on those juxtaglomerular cells to secrete our renin. So here we have our drop in blood pressure, and here we have our kidney. Kidney secretes renin. Already in the blood, we have angiotensinogen. So this is a plasma protein, or a precursor to a plasma protein. It's hanging out in the blood, doing its own thing, minding its own business. It's not active at this point. Renin and angiotensinogen, when they're together, we convert the angiotensinogen, into angiotensin 1. Notice that we go from 453 amino acids down to a 10 amino acid hormone here. Angiotensin 1 is going to continue to travel in the blood. As it travels to the lungs, it's going to come across ACE, or angiotensin converting enzyme. Angiotensin converting enzyme plus angiotensin 1 causes angiotensin 1 to become angiotensin 2. Angiotensin 2 is going to have widespread impacts. It is going to impact the brain, the cardiovascular system, as well as the adrenal glands, and ultimately the kidneys. So here we get thirst and drinking. Take a second to think about why being thirsty and drinking something is going to impact our initial stimulus. Right, so let's do this. Okay, so this is our stimulus. Right, we have a decrease in blood pressure. Our baroreceptor is going to be the part of our body that recognizes that stimulus. So then it sends messages to the nervous system, and the nervous system initiates a response. The initial part of the response is the kidneys with secretion of renin. The second part is going to be the conversion of angiotensinogen into angiotensin 1. The third part is going to be the conversion of angiotensin 1 into angiotensin 2. Only after we get angiotensin 2 do we have our effectors actually doing something. And so what is happening here is we are attempting to return to homeostasis. So you may be looking at this and you may realize that this is a negative feedback loop. Once we have an elevated blood pressure, we are going to turn off secretion of renin, we're going to turn off angiotensin 1 and 2, and we're going to stop this whole process. So angiotensin 2 on the cardiovascular system. Oh, I know what I was talking about. Got distracted. So when our blood pressure drops, we have low blood pressure. One way that we can help fix that or bring it back up is by adding blood volume or adding fluid to our system. That's where this drinking and thirst mechanism comes in. We actually add water back into the blood vessels. That increases our blood pressure. Angiotensin 2 is also going to act as a vasoconstrictor, so we close up our blood vessels, increases blood pressure, and it's also going to impact the kidneys. Now, what it does on the kidneys is usually through the production of aldosterone, which comes from our adrenal glands. The aldosterone is going to act on our collecting ducts and help in our distal convoluted tubules and result in water and sodium retention. So let's take a closer look at what aldosterone and ADH are doing in the body to get a better view of that. Looking at aldosterone, we should already know most of this, but I did want to review it since it's so important in kidneys. We call it our salt retaining hormone. That is because its primary function is going to be this one. So its main goal is reabsorption of sodium. When we reabsorb sodium, remember sodium sort of acts as a way to change osmolarity, and therefore water follows it. It also changes charge distribution or electrical distribution because it's positive. When we move it from the renal fluid back into the body, we are going to have negative charges or anions that want to follow it. And the main one is going to be chloride. So aldosterone is really working on sodium. Byproducts of that are going to be reabsorption of water and reabsorption of chloride. And so that's why we call it our salt retaining hormone. It is also involved in decreasing urine output and increasing blood volume because we pull water back out of the urine. So let's sort of walk through what we have going on here. It's going to be secreted by the adrenal glands, particularly that cortex region. Its main trigger is going to be this top one. So if we have low blood sodium concentrations or we have high potassium concentrations, we're going to get secretion of aldosterone. We did also just talk about how it is involved in the RAA process or RAA pathway, and so that is another way that we can trigger secretion of aldosterone. So here, let's sort of see what we have. Okay. So we're just going to start over here at 1 and basically follow these steps through. We have dehydration, we have lack of sodium, or we have loss of blood in general, and all of those things are going to result in a decrease in blood volume. Decreased blood volume causes decrease in blood pressure. Here's where we get our juxtaglomerular cells secreting renin. Renin plus angiotensinogen gives us angiotensin 1. Angiotensin 1 plus ACE gives us angiotensin 2, right? The results of that are going to be increase in secretion of aldosterone by the adrenal cortex. In the kidneys, we get sodium and water reabsorption and increased secretion of potassium and hydrogen into the urine. increase blood volume, and then blood pressure returns to normal, and we can turn off our secretion points. So that is sort of the overview or reminder of what aldosterone does. I want to be very clear that aldosterone and ADH function differently. Aldosterone is all about that sodium, all about sodium. ADH is more about actual water retention. So we use two different mechanisms. Here we're using sodium. A byproduct of pulling that sodium back into the body is absorption of water and chloride ions. So I'm actually going to sort of just skip over this natriuretic peptides. They're coming from the heart, and they also respond to high blood pressure and help regulate urine production. But what I want to pay more attention to is number 2, antidiuretic hormone, because we just talked about aldosterone. I want to give ADH its time. ADH is secreted by the posterior pituitary, so that means that it's made in the hypothalamus and then stored and secreted by this organ. This time it's being secreted in response to dehydration. So if we want to talk about what the actual stimulus for secretion is, and actually if we want to go even a step further, we would say, well actually right here, when we have a decrease in water or a decrease in blood volume or dehydration, we get an increase in osmolarity. Oops. And so when we get an increase in osmolarity, what we're going to do is ADH is going to act on primarily the collecting ducts, but also the distal convoluted tubules. It's going to result in, it upregulates aquaporin production and insertion into these parts of the kidneys. Aquaporins allow water to move out of that tubule and back into the body very easily. So the more aquaporins we have, the more water we hang on to. Okay, and I'm also going to sort of skip over parathyroid hormone. I really want you to focus on the RAA pathway, aldosterone, and ADH. And so here we just have sort of the breakdown of the different ways that we regulate or deal with low blood pressure in the kidneys. We have our intrinsic mechanisms. So these are autoregulation, so simply constricting our blood vessels or dilating our blood vessels, and simply using our juxtaglomerular system, we can regulate the kidneys and their production. And this is low blood pressure. Actually, a lot of what we've talked about is sort of high blood pressure, so that's why these look a little bit different. And then our extrinsic mechanisms, we have aldosterone or renin-angiotensin-aldosterone, as well as our neural control. So these would be outside of the kidneys. Okay. All right, and so the very last thing that I'm going to talk about is just how hydration levels are involved in determining urine concentration. And so I hit on this again, like at the very first lecture where I was talking about urine composition and how much water versus other things we had. The amount of fluid that you intake does change the concentration of solutes in your urine. So you may notice if you have a day where you don't drink any fluids for whatever reason, by the end of the day your urine's going to be very dark. You're probably not going to be urinating very much. If you drink a lot of fluid throughout or over the course of the day, you're going to have urine that is very abundant. So you're going to be urinating a lot, and it's also going to be nearly clear. That would be hypotonic urine. Hypotonic tells us that it has a high volume of water and a low concentration of dissolved solutes. So here would be that concentration as low as 50 milliosmoles per liter. Dehydration, on the other hand, we have very hypertonic urine as well as low volume. So that means that we have an increase in well, that should be urine osmolarity would be very high. This actually does relate to blood osmolarity, because when we have high blood osmolarity, we try and hang on to more water, which is going to enhance this dehydration effect. So basically, the more water you drink, the further you push away from dehydration and towards what we call diuresis, whereas if you do not drink a lot of water, you can put yourself closer to this dehydration mark. Okay, so obviously it took me 14 little mini lectures to get through the urinary system, and there's actually more that we could talk about. I've taken out some content that I've gone over in the past because I simply want us to get the basics at this point. And so I have put together, I know that there's resources posted on MO2, all of those supplemental resources that you can go to. Here are some additional links, and I know some of these are duplicates, but they may be useful in your studying, so I would encourage you to use these as well. Okay, and again, sort of given our situation, we are not going to do acid, base, and fluid balance right now. We are going to go right into the reproductive systems for the sake of time and sanity. And so with that, I leave you. The next thing that you'll be doing is exam 3. And after that, we will move into the reproductive systems, and we're pretty much rounding out our semester. So I hope it is all still going okay.